The universe is cold where sunlight cannot reach. Between stars, the temperature of empty space sinks below 3 degrees above absolute zero, a silent ocean stretching across billions of kilometers. A spacecraft drifting here feels no breeze, no sound, only the constant pressure of particles striking its hull like sand in slow motion. Ahead lies a red dwarf barely visible to the human eye, its dim light traveling more than 4 years before reaching us. Proxima Centauri, our nearest stellar neighbor, waits on the far side of that darkness. We measure the distance in light years because ordinary units fail. How do we carry humans across such a gulf? What engines change centuries into decades? Why do some concepts promise weeks rather than lifetimes? Tonight, we explore the paths carved by physics and ambition. Generation ships that endure 400 years, fusion vessels crossing in mere decades, and exotic drives that compress the journey into days if their equations ever meet reality. If you enjoy journeys into deep space, please like and subscribe and tell us where in the world you are listening from. Let's begin. The space around Earth feels gentle because our star protects us. Solar wind forms a bubble of charged particles, a sheath that deflects cosmic radiation like a shield of invisible rain. Beyond this boundary, the space between stars is harsher and older. Dust grains drift alone for millions of years. Cosmic rays strike without pause. A ship heading toward Proxima b must pass through this frontier, where the sun's influence fades and the void becomes a ruler. This is the starting point of every interstellar mission, the moment we step beyond familiar gravity, beyond the warmth of our home, and into conditions no spacecraft has yet survived for generations. This protective region is shaped by plasma, leaving the sun at hundreds of kilometers per second. The particles move outward in every direction, forming the heliosphere. Within it, radiation is moderated, spacecraft electronics degrade slowly, and cosmic rays are partially deflected. No one designed this boundary. It emerged naturally from stellar activity, like a tide extending from a shore. At the edge of this tide, solar wind meets the gas between stars and loses its strength. The result is a transition zone, and eventually, a crossing. That crossing is not loud or dramatic. Voyager 1's passage into interstellar space was not announced by alarms or sudden motion. Its instruments simply began detecting more energetic particles from outside the solar system and fewer from our own star. That change marked a one-way threshold. Everything beyond it is older, colder, and less forgiving. Spacecraft cannot rely on solar power there. Radiation shielding becomes a permanent requirement. Time delays stretch communication into hours, then years. A mission to Proxima b must survive in this environment not for months, but for decades. That is why the crossing matters. Inside the heliosphere, engines may fail and engineers on Earth can still intervene. Beyond it, problems must be solved on the ship. Autonomy becomes necessary, not optional. Navigation, maintenance, medical systems, and propulsion must keep functioning far from assistance. Interstellar space is not a wall, it is a test of self-sufficiency. The vacuum itself becomes a hazard. At velocities approaching 1/10 of light speed, a dust grain impacts like a bullet. A particle too small to see with the naked eye becomes plasma on contact, releasing heat that melts metals and severs wiring. Ships require shielding strategies designed to sacrifice material, vaporize debris, or deflect charged particles long before they meet crew compartments. Nothing in low Earth orbit prepares us for these impacts. They are consequences of attempting to move at relativistic speeds. Radiation is equally indifferent. Cosmic rays travel close to the speed of light, forged in old supernova shockwaves or energetic galactic events. They tear through electronics, corrupt data, and damage biological tissue on a microscopic scale. Human cells can repair small genetic breaks. Beyond the heliosphere, the damage accumulates faster than nature evolved to handle. Shielding increases mass. Mass slows acceleration. Every kilogram becomes a negotiation between survival and speed. We leave our star not because we are careless, but because exploration has always demanded we accept unknown landscapes. Ancient seafarers left coasts. Pilots trusted aircraft over oceans. Interstellar travelers will drift into regions where sunlight becomes a memory. The sun is still there, a faint lantern among stars, but its warmth no longer reaches through the hull. To reach Proxima b, we must cross this threshold. We must accept conditions shaped not by our star, but by the silent rules of the galaxy. The journey begins not when engines ignite, but when the influence of home becomes too weak to protect us. Beyond that point, survival depends on what we carry, what we engineer, and how prepared we are to confront space that has never known human life. 4 light-years of emptiness are not an expanse we can walk or fly across. They are time-made physical photons moving relentlessly, crossing ancient space before gently tapping detectors on Earth. When we try to imagine this journey, our minds reach for roads and oceans. But these metaphors collapse under the scale. Traveling to Proxima b means enduring a distance so vast that guidance, communication, and patience must be measured not in hours or days, but in decades and lifetimes. Understanding the shape of this separation forces us to accept a fundamental truth. The space between stars is not a gap, it is a landscape. If you could watch a beam of light leave Earth toward Proxima Centauri, nothing about its path would feel dramatic. No colors swirl, no shockwaves ripple. It simply moves, second after second, through a thin haze of gas and dust that barely acknowledges its presence. Yet even at the fastest speed allowed by nature, that beam needs more than 4 years to complete the crossing. For a spacecraft, the crossing stretches much longer. The distance is not a line to be drawn, it is a span of time that weighs on every decision. Our instincts try to shrink this gulf with comparisons. We picture long-haul flights, ocean crossings, circumnavigations of Earth. But those journeys all share something this one does not: feedback. You can see the horizon change, feel weather shift, track landmarks as they appear and vanish. Between stars, there are no mountains or coastlines. A ship's surroundings look almost identical at launch and halfway through the voyage. Progress becomes something you infer from instruments, not from experience. This has consequences. Navigation can no longer rely on intuitive cues. It depends on precise measurements of starlight, tiny shifts in frequency and position that reveal motion against the galactic background. Time delays turn course corrections into long-term planning instead of quick responses. A mistake in the early years might only be discovered decades later, when it is far too late to reverse. Distance also reshapes communication. On the scale of the solar system, signals take minutes or hours. Commands can be sent, results can be checked, and strategies adjusted. At interstellar ranges, each message becomes a commitment. A question to a ship near Proxima takes years to arrive, and the reply takes years more. Dialogue stretches into something closer to archaeology. By the time you read the answer, the situation that prompted the question may no longer exist. Speed, too, becomes abstract. At 100 kilometers per second, a speed beyond any current crewed mission Proxima b still lies tens of thousands of years away. Boosting to 1% of light speed cuts that to around 4 centuries. But even that improvement is longer than the entire history of modern science. Numbers we treat lightly on paper become lifetimes in practice. In that sense, the landscape between stars is defined less by what is there and more by what is not. There are no refueling stations, no repair depots, no quick returns. Every kilogram of material and every line of code must be chosen, knowing that once the ship leaves, the distance will not allow easy correction. The void is not hostile in the way a storm is hostile. It simply offers no help. Seeing the space between here and Proxima b as a landscape changes the question from how far is it to what must survive inside it. Engines, habitats, guidance, culture, memory, all must endure not a path but an era. Only when we accept that 4 light-years are measured in time, not imagination, do our plans begin to match the true shape of the distance. Inside a rotating vessel, centrifugal force becomes gravity. Floors bend with the curve of the hull, and fields of wheat grow in gentle arcs beneath artificial skies. A generation ship does not rush, it endures. The engines provide a steady push, reaching speeds of roughly 1% of light. At that pace, the journey to Proxima b stretches to about 4 centuries. Babies will be born who never see Earth. Entire communities will age and pass their responsibilities to the next custodians of the mission. The ship becomes a world unto itself, a stable ecosystem drifting among stars. Life aboard such a vessel is defined by continuity. Water circulates in closed loops, filtered and condensed through membranes and tanks. Carbon cycles through crops, compost, and air scrubbers. Light is rationed according to the needs of photosynthesis, not weather. Every square meter of habitat serves a function, whether biological, social, or mechanical. There is no wilderness, no unused terrain. The ship is a living system engineered to avoid fragility. Agriculture becomes architecture. Rows of hydroponic trays line curved corridors, each one tuned to provide calories reliably for decades. Fruit trees dwarf beneath ceilings, pruned to conserve space and energy. Machinery tends soil substitutes, dispensing nutrients based on sensor readings rather than intuition. These are not rustic farms. They are laboratories of survival. Their purpose is to produce food as predictably in year 390 as in year 3. The crew of a generation ship does not speak in terms of missions or expeditions. They speak in terms of stewardship. The first generation will remember launching from the solar system, but the second will not. Their reference points shift inward toward classrooms, markets, rituals, and maintenance schedules. Home becomes the vessel and its rotation, not a distant planet they have never seen. In this way, identity is transmitted like oxygen, constantly circulated, constantly renewed. Governance must evolve as predictably as water or power. Decisions cannot be the product of crisis lurches or charismatic leaders who vanish after a decade. Institutions are required educational systems that teach the principles of propulsion and life support, councils that monitor genetic diversity, committees that allocate living space as births and deaths change population. Self-rule is not ideology. It is a mechanism to keep the ship's culture and engineering aligned. The psychological landscape of such a journey is unfamiliar. Earth provides variety, a spectrum of seasons, weather, and landscapes that change without human intervention. A generation ship is more static. Its corridors do not erode, its stars do not visibly move. The same pathways are walked thousands of times. Meaning must be generated internally. Holidays marking milestones of maintenance, ceremonies for new repairs, traditions that frame conservation not as restriction but as legacy. Failure is communal. A damaged greenhouse is not an agricultural issue, it is a population issue. A failed oxygen recycler is not an engineering mistake, it is a threat to nearly everyone aboard. Responses must be quick and coordinated, and they must be taught to every child from the beginning. Knowing how to replace a seal, interpret a sensor reading, or diagnose stress fractures becomes as fundamental as literacy. Survival on a generation ship is not a specialty, it is culture. Education is therefore continuous. Students learn physics not to become scientists but to maintain reactors. They learn ecology not to document species but to balance nitrogen cycles in hydroponic chambers. History includes Earth, but it gradually becomes a prelude. The story that matters is the one unfolding in steel walls and rotating habitats. For the last generation aboard, Proxima b will not be an abstract endpoint. It will be the horizon at the end of their lineage. The journey is slow, but it is not stagnant. Life aboard a generation ship moves forward in the same way seasons progress on Earth, through patterns repeated intentionally until they become instinct. The vessel is no longer transportation. It is civilization expressed as engineering, built to persist until its descendants step onto soil no one alive remembers. Fusion propulsion begins where chemical engines end. Instead of oxidizer and fuel, fusion pulses compress hydrogen isotopes until they behave like the heart of a sun. Each pulse erupts behind the ship, producing thrust through magnetic nozzles designed to survive plasma hotter than any earthly furnace. These bursts accumulate, pushing the vessel toward a tenth of light speed. At such velocities, the journey shrinks to decades. But this approach demands immense engineering discipline. Fuel pellets stored by the millions, reactors that fire thousands of times per minute, and hulls armored against dust that strike like needles of fire. To understand why fusion matters, imagine riding a bonfire into orbit. Chemical rockets release energy by rearranging molecular bonds. Oxygen meets fuel, heat is produced, exhaust rushes outward. But in nuclear fusion, the bonds of atomic nuclei are altered. Hydrogen isotopes compress until they merge, releasing energy 1,000,000 times greater per kilogram than chemical fuel. It is the same process that gives stars their brilliance. On a spacecraft, that furnace must be contained into repeating, controlled pulses, only millimeters wide and microseconds long. The preferred fuels are deuterium and helium-3. They fuse cleanly, producing high-energy particles and minimal radioactive waste. But helium-3 is rare on Earth. It may be mined from gas giants or the lunar regolith, or bred through nuclear reactions, adding complexity before the ship ever leaves the solar system. Once stored, the pellets sit in cryogenic vaults, waiting to be injected into a reaction chamber where lasers or magnetic fields compress them faster than they can unravel. Each pulse forms a miniature star, igniting for an instant before cooling. The reactor shields itself behind nested magnetic fields. They bend plasma like wind around the hull, turning explosive heat into directional thrust. The nozzle is not metal in the conventional sense. It is a cage of magnetism that channels particles outward without melting. Behind the vessel, exhaust becomes a ribbon of blue-white radiation disappearing into vacuum. Nothing about this process resembles a traditional rocket. The engine is a controlled stellar storm. At 1/10 the speed of light, travel becomes a balance of energy and endurance. The pulses must occur without interruption for months or years. The engine cannot rest. If it does, the ship drifts without the ability to slow or correct course. The craft's internal systems monitor every firing event, absorbing vibrations, dissipating heat, and adjusting fuel consumption. Electronics must survive the electromagnetic shock of their own propulsion. Radiators extend like wings, shedding waste heat into space, so the reactor does not cook the habitat modules. These speeds introduce their own dangers. A grain of dust becomes a plasma lance on impact. To protect its forward section, the ship may carry a sacrificial shield layers of carbon or ice that slowly erode. Other designs propose electromagnetic bows that sweep particles aside before collision. The engine is not the only challenge. The velocity it grants exposes the vessel to physics rarely encountered by humanity. A fusion-driven mission also changes how we think about time. 400-year voyages become 40. A single generation might construct the ship, and the next might step foot on foreign soil. Scientific returns arrive within a lifetime rather than across epochs. Yet this acceleration carries responsibility. Unlike probes, crewed fusion ships cannot simply pass a star at full speed. They must decelerate. The energy required to slow from 0.1 c rivals the energy required to accelerate to it. Half the mission's mass may be dedicated to braking. Without it, the destination becomes a blur. Fusion propulsion is not a promise of easy travel. It is a willingness to build engines that imitate the stars, accept the risks they create, and endure the unforgiving pace they enable. If humanity ever attempts to reach Proxima b in decades rather than centuries, it will likely be aboard a vessel powered by suns locked in chambers of metal and magnetism. A light sail is a mirror stretched across emptiness. Lasers on Earth strike it, pushing it forward with photons, the way wind pushes a sail at sea. There is no engine, no combustion, no reaction mass, only momentum transferred from beams of light. Once accelerated, the sail coasts freely, its payload gliding at a fraction of light speed. 20 years later, the probe could pass Proxima b. It will not slow. It will not orbit. It will simply glance at another sun and continue into deeper night. The elegance of this method lies in its simplicity. Power at home, speed abroad. The physics behind this gentleness is direct. Light has no mass, but it carries momentum. When photons strike a reflective surface, they bounce, reversing direction. That reversal pushes against the sail, transferring tiny amounts of force. One push is insignificant. Trillions upon trillions of photons, sustained for minutes or hours, accumulate into thrust. The sail does not roar or rumble. It moves as if the universe itself were lifting it along a silent wind. A laser sail must be extremely light. A structure built for human crew would collapse under its own weight, snapping like foil in a gale. Instead, the concept calls for a payload measured in grams. Thin electronics, hardened sensors, miniature guidance systems. The sail unfurls wider than a house, but the craft behind it is barely larger than a coin. These proportions are dictated by the nature of propulsion. The lighter the craft, the more each photon matters. Acceleration occurs close to home, where resources are abundant. Arrays of lasers positioned across continents or mounted in orbit focus their beams into a stream of relentless pressure. The sail begins slowly, then faster, climbing to tens of thousands of kilometers per second in minutes. During this phase, the vessel experiences no atmosphere, no drag, only raw momentum. The ship does not burn fuel, it leaves nothing behind but light. Once the sail is out of range, the propulsion ends. The probe becomes a bullet coasting through the void, carried by its own acquired speed. In the vacuum between stars, no friction slows its motion. With no fuel to ration and no engine to maintain, it moves onward under inertia alone. Deceleration, however, is not part of the design. Stopping at Proxima would require energy equal to what launched it. Without onboard thrust, the craft becomes an observer, passing through a system like a meteor. That reality shapes the mission. A laser sail does not conduct exploration in a traditional sense. No orbital insertion, no landings, no return. Its sensors must gather everything during the flyby. Planetary atmospheres, star flares, magnetic fields, dust. It must compress decades of travel into minutes of observation. A camera may capture the glow of a red dwarf, the silhouette of a planet, or the arch of an exoplanet's aurora. Then the probe disappears into darkness, leaving only a stream of data racing back to Earth. The simplicity of this propulsion hides heavy challenges. The sail must survive laser intensity that would vaporize most materials. It must reflect light without tearing or twisting. Guidance systems must correct microscopic misalignments because a fraction of a degree becomes millions of kilometers off course over decades. Even dust can be lethal. A particle no larger than a grain of salt, striking at 1/5 light speed, becomes a blast of plasma that could punch through the sail and destroy the payload. Communication is equally unforgiving. The probe must send signals back across more than 4 light-years with only a tiny power source. Every watt counts. Data must be compressed, error-corrected, and transmitted in narrow windows when its antenna points toward Earth. Any failure may result in silence. For all these limitations, the laser sail remains our clearest path to reach another star in a human lifetime. It does not wait for exotic fuels or reactors that mimic the heart of suns. It does not ask us to bend space-time or rewrite physics. It asks only that we harness light, a resource we already understand, and let momentum carry the smallest of explorers into the greatest of distances. Human bodies evolved under one atmosphere of pressure and modest radiation. Interstellar travel removes both. At high speeds, cosmic rays pierce cells, breaking DNA strands faster than they can repair. Water, polymer layers, or electromagnetic fields may serve as shields, but protection increases mass and complexity. Even movement becomes dangerous. A collision with a grain of dust at tens of thousands of kilometers per second would release energy like a small explosion. To send humans to Proxima b is not simply to build a ship, it is to build a habitat capable of preserving life in the harshest environment known. The vacuum between stars is not merely empty. It is chemically and biologically indifferent. There is no breathable air outside the hull, no gravity to stimulate bone growth, no natural safeguards against radiation. Bodies accustomed to planetary cycles begin to weaken in microgravity. Muscles atrophy, calcium drains from bones, and blood shifts toward the chest. On a short orbital mission, exercise and medication can counter this decay. On a voyage lasting decades, countermeasures must become architecture. Rotating habitats, spinning rings, and environments designed to mimic gravity through motion. Radiation is a more persistent threat. Cosmic rays are not gentle beams, but atomic nuclei accelerated to near light speed by ancient explosions. They slice through flesh and electronics alike, leaving trails of damage that cells struggle to mend. DNA attempts repair, but errors accumulate, like scratches on a disk replayed too many times. Over long durations, the risk of cancer rises, nervous tissue suffers, memory, balance, and cognition may deteriorate. No shielding is perfect, only gradients of risk. To reduce exposure, designers consider layers of water, carbon composites, or hydrogen-rich polymers. Materials like these slow charged particles, dispersing their energy. Some propose burying crew quarters deep within water reservoirs or cryogenic tanks, turning necessities into armor. But every kilogram of shielding must be launched, accelerated, maintained, and repaired. Mass becomes a biological tax. The safer the crew, the slower and heavier the vessel. Not all hazards come from radiation. Humans require rhythm day and night, seasons, the psychological ballast of a horizon. Interstellar transit provides none. Beyond the solar system, the stars outside hardly move, their positions frozen in the black. Crews live in environments of consistent hum. Ventilation systems, waste processors, gyroscopic bearings. Without carefully managed cycles of light and darkness, sleep fragments, attention drifts, motivation erodes. A mission that spans years tests not the body alone, but the mind's ability to find meaning in repetition. Food adds its own burden. Fresh produce cannot arrive by resupply, and nutrient stores degrade. Vitamins lose potency, oils oxidize, and canned goods become unsustainable. Systems must grow their own food, recycling water and minerals repeatedly. A failure in one tier, a fungal bloom in a hydroponic bay, a bacterial imbalance in air scrubbers can echo throughout the environment. On Earth, ecosystems recover autonomously. On a starship, ecosystems must be tuned like instruments. Then there is collision. A dust particle at relativistic speed does not dent a hull. It becomes plasma, spreading heat into surrounding structure. The shock waves can trigger cascades, insulation burns, wiring melts, compartments depressurize. The threat is not the grain itself, it is its velocity. Protecting life requires sacrificial shielding, debris sensors, and expected losses. Micrometeoroid strikes are not accidents, they are statistical certainties. For these reasons, a ship carrying humans to Proxima b cannot simply be a vessel with rooms and engines. It must be a medical environment, a psychological refuge, and a biological fortress. Every wall, surface, and interface must serve the purpose of sustaining living systems through years of exposure. The goal is not comfort, it is continuity, ensuring that fragile bodies designed for beaches, forests, and gravity can endure a corridor of space where none of those things exist. A spacecraft is a furnace surrounded by infinite cold. Humans, electronics, and fusion reactors release heat constantly. Without air or water to carry it away, thermal energy accumulates until systems fail. Radiators must glow softly into the void, their panels stretched like wings to bleed photons. In the deep dark, temperature is a negotiation. Too much insulation and the craft overheats. Too little and components freeze. The challenge is not warmth or cold alone, it is balance in a place where equilibrium must be engineered from first principles. Heat behaves differently in space. On Earth, convection is our invisible partner. Warm air rises, cool air descends, and thermal gradients smooth themselves out. Even in spacecraft orbiting Earth, heat diverts through fans and ventilation ducts. But between stars, there is no medium to carry warmth away. Only radiation remains. Thermal photons must be shed directly from the hull, traveling outward until they fade into nothing. This simple fact defines spacecraft geometry more than aesthetics or aerodynamics ever could. Radiators are not optional accessories, they are survival organs. Large rectangular panels unfold from the ship like petals, built from materials engineered to emit infrared efficiently. Their surfaces are dark, textured, and carefully coated. They are the opposite of solar panels. Instead of collecting energy, they release it. A generation ship crossing the void might dedicate more area to thermal management than to propulsion or habitat. The emptier the surroundings, the more deliberate the shedding of heat must be. Engineers design thermal pathways in layers. Heat from crew compartments travels through pipes filled with coolant, then into pumps, then into radiator lines. A blockage, even a minor one, can raise local temperatures and accelerate wear on nearby systems. Electronics, especially high-density processors, suffer when warm. Their efficiency drops. Their failure rate climbs. In the absence of intervention, heat compounds until it becomes a slow-burning catastrophe. Fusion propulsion intensifies the problem. A reactor producing thrust at 1/10 of light speed is not a small device. It generates temperatures rivaling stellar interiors, channeling them through magnetic nozzles to avoid melting metal. The engine's waste heat saturates the ship long after firing stops. Radiators must grow. Cooling loops multiply. Habitat decks sit behind layers of insulation not to keep passengers warm, but to keep them cool. Spaceflight becomes an exercise in patience, waiting for the vessel to shed enough energy to remain stable. Cold presents its own dangers. In shadowed corridors or shielded bays, temperatures fall toward the space outside. Fluids thicken. Plastics lose elasticity. Metals shrink, altering tolerances and cracking seals. A ship that cools too aggressively becomes brittle, like glass exposed to sudden frost. Thermal systems must prevent freezing in the same way they prevent overheating, warming lines, or circulating coolant, even when no human feels cold. Interstellar thermal management is a constant seesaw, never too much, never too little. Micrometeoroid impacts turn heat management into hazard response. A collision creates a brief flash of plasma, injecting energy into structural materials. Nearby sensors register a spike, then a shockwave propagates through hull plating. Radiators close to the strike can blister. A panel may curl or warp, reducing its emissivity. Repairs require patience. Replacing a radiator wing in deep space is not a momentary task, but a multi-week operation. Executed cautiously so that no system overheats while waiting. Humans sense temperature as comfort, but a ship senses it as survival. The balance between heat generation and heat rejection becomes a rhythm deeper than life support, deeper even than propulsion. The vessel's heart is its thermal equilibrium, its pulse measured in watts, its breath the soft glow of radiators that scatter warmth into an endless night. In interstellar travel, warmth is not an asset or luxury. It is a burden that must be managed with the precision of a surgeon. Fission reactors powering electric thrusters provide gentle acceleration, but they are steady teachers, not sprinters. They ionize propellant, pushing it from their engines in a constant whisper. Over months or years, a ship gains speed slowly, its progress built on endurance. Nuclear thermal designs heat hydrogen until it bursts from the nozzle, delivering thrust stronger than electric engines, but still far weaker than fusion. These technologies may take us to Mars, the moons of Jupiter, or the outer planets. Across interstellar gulfs, they fall short, stretching travel to thousands of years. The strength of nuclear propulsion lies in patience. Electric thrusters, Hall-effect drives, ion engines, and variants operate with extraordinary efficiency. They expend a tiny amount of propellant to gain velocity, accelerating ions to tens of kilometers per second. The thrust is barely enough to push a sheet of paper, but it does not stop. Day after day, the ship inches faster until its speed becomes meaningful. Spacecraft like Dawn demonstrated the principle around asteroids: weak thrust, long duration, steady achievement. In the interplanetary realm, this formula works beautifully. But interstellar distances impose harsher arithmetic. Even at their best, nuclear electric engines approach velocities measured in thousandths of the speed of light. At that pace, Proxima b is not a destination, it is a timescale that stretches across civilizations. A probe that departs now would arrive in an era where human societies, languages, and technologies might be unrecognizable. Nuclear thermal propulsion offers a different trade. Instead of accelerating ions, it heats liquid hydrogen through a fission reactor until the gas erupts from the nozzle. The exhaust velocity is far higher than chemical rockets can achieve, and missions to Mars might be cut from months to weeks. Crews feel acceleration more tangibly. A ship using this method has muscle, not subtlety. But even here, the limit emerges. The energy released by fission is finite. It is nowhere close to the density of fusion. The result is an engine that shines within a planetary neighborhood, but dims when confronted with a 4-light-year ocean. Another problem rises quietly. Mass. Reactors require shielding. Power systems require radiators. Propellant tanks expand to hold the cryogenic hydrogen that makes nuclear thermal thrust possible. Each component has weight, and weight governs acceleration. Designers can increase power, but power demands sturdier structures, thicker walls, larger radiators. The result is a cycle in which each improvement invites another penalty. Nuclear propulsion is powerful, but it is not agile. There are attempts to bridge the gap. Concepts like bimodal reactors provide engine thrust when needed and electrical generation when coasting. Others propose nuclear tugs, vessels that ferry payloads from planetary orbits to deep space trajectories. These systems could reshape human exploration of our solar system. They could bring mining platforms to the outer planets or carry habitats across the icy moons. But none of them evade the math of interstellar travel. The speeds they produce are impressive only by the standards of planets circling a single star. Even if we had flawless nuclear reactors and perfect reliability, the distance to Proxima b would remain stubborn. A ship leaving Earth at nuclear electric velocities does not merely take lifetimes to arrive, it spends longer than some civilizations have existed. The strength of nuclear power is endurance, not momentum. It teaches us to think long, to conserve fuel, to travel by accumulation. Against the gulf between stars, endurance becomes a limitation. This does not make nuclear propulsion obsolete. It makes it foundational. Before we ignite fusion pellets or fling light sails into the void, nuclear engines can build the infrastructure around our own sun shipyards in high orbit. Ice harvesters on moons, research stations beyond Neptune. They expand the horizon of what is reachable. They train us to operate far from Earth, but when the journey measures light years instead of millions of kilometers, nuclear engines remind us of a sobering truth. Some distances cannot be crossed slowly. Interstellar dust is sparse, but speed multiplies its danger. At a fraction of light speed, even a particle the size of a pepper grain carries enough kinetic energy to puncture hull plating. Impacts release plasma that chews through metal. Shielding must be layered, sacrificial, or electromagnetic designs that allow dust to vaporize safely before striking vital systems. Traveling to Proxima b means accepting collisions as inevitabilities, not accidents. Every meter becomes a negotiation between momentum and survival. At the velocities required to traverse light years within decades, mass transforms. A particle that floats harmlessly in the void, at normal spacecraft speeds becomes a projectile with destructive force. Its kinetic energy scales with the square of velocity. 10 times faster is 100 times more violent. A grain invisible to the naked eye fragments into bright plasma on impact, transferring heat and force into whatever lies behind the hull. Spacecraft designers treat these collisions not as rare events, but as background radiation, always present, always accumulating. This reality forces careful engineering. One approach is sacrificial shielding. Layers of foam, graphite, or ice sit ahead of critical compartments. When impacted, they vaporize first, absorbing energy and slowing debris. The next layer takes the weakened strike, and the next until the violence dissipates. The method resembles ablative heat tiles on re-entry vehicles, only inverted. Instead of protecting against atmospheric friction, the tiles protect against micrometeoroid storms moving at relativistic speeds. Beyond physical shielding, there are magnetic concepts. Charged particles respond to electromagnetic fields, bending their trajectories. A ship can project a magnetic bow ahead of its hull, redirecting ionized dust before it strikes. This does not help against every grain. Many particles are neutral, or become ionized only after impact. But it reduces exposure, particularly to the constant rain of atomic fragments accelerated across galactic space. Protecting a ship is never about deflecting everything. It is about lowering risk until the statistics become survivable. Detection is another tool. Radar and LiDAR struggle in the void. Targets are too small, the distance is too great, and the relative speeds extreme. A pepper-sized grain moving at tens of thousands of meters per second crosses the detection window in milliseconds. Instead, some proposals look ahead with particle counters sensors that register high-velocity impacts on forward plates. They warn of dense regions and prompt course changes. It is not elegant, it is practical. Steer around the danger, because shielding has limits. Even with foresight, collisions cannot be eliminated. Dust is older than humanity, forged in the shells of ancient stars, scattered through nebulae, compressed in stellar winds. It drifts in filaments, clouds, and diffuse streaks. A ship crossing 4 light-years will plow through millions of grains, most too small to notice, some powerful enough to end a mission instantly if left unmitigated. When designers consider interstellar travel, they do not ask whether a ship will be struck, they ask how often and what happens next. This vulnerability extends into crew psychology. Living aboard a vessel that meets constant micro-impacts reshapes how inhabitants perceive safety. The sound of collisions, if it ever reaches the habitat, would be a reminder that space is not empty, only indifferent. Maintenance teams become guardians, inspecting forward shields for fractures, replacing panels that have thinned from repeated ablation. These tasks are not dramatic. They are routine, woven into the rhythm of life, like tending a garden or repairing a road. At lower speeds, Earth's orbit provides a template. Satellites encounter micrometeoroids often, each strike documented in small pits on solar arrays or insulation. But near-relativistic ships leave this comfort behind. Their environment is not orbital debris. It is the diffuse remains of stellar evolution, moving so fast relative to the vessel that impact energy becomes catastrophic. A ship pursuing Proxima b must be armored against the physics of its own ambition. In interstellar flight, dust is not hostile. It is unintentional, ancient, and constant. Its danger comes from motion, not malice. To survive, a ship must treat the void as a field of hazards and move through it with respect, shielded, monitored, and resilient. The journey is not simply a race against distance. It is a steady conversation with particles older than Earth itself. Communication is bounded by physics. A message sent from a ship halfway to Proxima would take more than 2 years to reach Earth, and any reply would arrive 2 years after that. Guidance must be autonomous. Repairs must be immediate. The crew or its artificial systems cannot wait for permission. Interstellar flight isolates travelers not by walls or distance, but by time itself. It turns every decision into a statement of responsibility. When spacecraft operate near Earth, communication feels instant. Commands travel in seconds, telemetry streams back continuously, and ground crews adjust course with live data. Even probes at Jupiter remain comprehensible. Signals cross the void in under an hour. Those time delays feel inconvenient, not existential. At interstellar distances, delay becomes a governing law. A crew requesting technical advice would receive help only after years, long after the crisis had evolved. The flow of cause and effect stretches until it no longer resembles conversation. Time transforms knowledge. Engineers on Earth will always have more tools, more specialists, more data, but their insight arrives stale. The ship becomes the only place where problems can be solved. Diagnostics must be performed on board. Repairs must be designed and executed by the people who live beside the fault. Every maintenance action is irreversible because there is no one to confirm or correct it. Mistakes are not miscommunications, they are chapters of the journey written without revision. Communication itself becomes an art. Signals weaken across light years, scattering through interstellar dust and gas. Antennas must aim precisely, compensating for the motion of stars and the ship's own relativistic velocity. The vessel's transmitter cannot waste energy. It must compress images, telemetry, and crew messages into narrow bandwidths that survive the journey home. Each packet travels alone, bearing news across a gulf wider than human history. Earth's response carries its own weight. A transmission from home may speak in past tense events that occurred 4 years earlier. New discoveries, new governments, new philosophies, all arrive as delayed echoes. The ship's culture will drift away from Earth's, not through rebellion, but through the unavoidable erosion of synchronization. The crew experiences time as a river. The people they left behind experience them as a memory in transit. Artificial intelligence becomes an intermediary. A vessel may rely on decision engines that monitor thousands of sensors, interpret anomalies, and act before humans fully understand the problem. This is not convenience, it is survival. A coolant leak in a reactor, a pressure fluctuation in a greenhouse, or a software glitch in navigation cannot wait for Earthbound expertise. Systems must diagnose themselves, craft contingencies, and apply them without hesitation. Human oversight becomes strategic, not immediate. Even simple messages carry emotional weight. A berth aboard the ship, a scientific discovery, a vote for new leadership, each is transmitted to Earth, knowing that recipients are watching a past version of the crew. In return, passengers receive news of friends and loved ones they have not seen for years. Some will learn of death long after it occurred. The latency of grief extends across light years. The distance also changes diplomacy. If Earth authorizes a maneuver or requests a scientific survey, the crew may be in a different region of space by the time the instruction arrives. They may have already made a choice. Authority fragments not because command dissolves, but because command cannot arrive in time to matter. Interstellar voyages require autonomy by design, not by preference. Ultimately, traveling to Proxima b is not an exercise in reaching new coordinates. It is an exercise in thinking without immediate validation. A ship in deep space becomes its own world. Crew, machines, and memory navigating a corridor of light that stretches years in every direction. Communication does not bind them to Earth, it reminds them how far away Earth truly is. In rocketry, fuel is not only thrust, it is burden. Every kilogram of propellant demands structure to store it, engines to burn it, and mass to push it. The rocket equation traps designers in a loop. To go faster, you carry more fuel, but fuel increases mass and slows you. Fusion offers relief, generating enormous energy per gram, but it still requires vast reserves. Concepts that harvest interstellar hydrogen present alternatives, yet introduce uncertainty. Mass determines destiny, and every possible ship must grapple with this unforgiving law. A spacecraft is not a car carrying gas to refill along the way. There are no stations between stars, no places to top up. Every gram of propellant must be aboard at launch or manufactured on the journey. The deeper the mission, the heavier the starting point. Designers attempt to lighten tanks, compress fuels, or shape engines to use less thrust, but each innovation triggers another constraint. Tanks need insulation. Insulation adds weight. Weight demands more structure, which demands more fuel, which adds more weight. A ship begins to grow into the very challenge it is trying to escape. This is why even advanced propulsion starts with the math of reserves. Nuclear thermal rockets heat hydrogen to extreme temperatures, ejecting it through a nozzle to produce thrust. Hydrogen is efficient mass for mass, but storing it requires pressure or cryogenics. Either solution adds hardware and increases vulnerability. A leak, a valve failure, a crack in a line. Any of these becomes a bottleneck for acceleration or braking. The ship is not a simple projectile. It is a delicate balance between power and volume. Nuclear electric designs push the problem into a different form. They burn little propellant, but demand steady electrical power, heavy radiators, and reactors that last decades. The tank shrinks, but the engine room expands. The mass shifts, but it never leaves. Every propulsion method solves one issue and introduces another, like moving weight from one hand to the other. Fusion lowers the ratio drastically. A few tons of fuel can drive a ship far longer than any chemical or fission system could. Yet fusing isotopes reliably means storing them in precise quantities, protecting them from leaks, and firing them with equipment that survives the heat of a star thousands of times a minute. A fusion vessel may not need massive tanks, but it needs shielding, superconductor magnets, cryogenic lines, and firing chambers. The fuel becomes small, the infrastructure becomes large. Proposals for Bussard ramjets attempt to bypass fuel entirely. Instead of carrying hydrogen, the ship deploys enormous magnetic fields and scoops interstellar particles, funneling them toward a fusion core. In theory, the ship accelerates forever, harvesting the galaxy as propellant. In practice, the scoop's drag may exceed its gain. The ship may slow as it gathers fuel. What looks elegant in equations becomes uncertain in the dust-laden corridor between stars. The risk is not philosophical. A ramjet that cannot outrun its fuel intake becomes a drifting monument to optimism. Even braking is governed by propellant. A ship that accelerates with fury must decelerate with equal patience. Without a way to shed velocity, Proxima b becomes a flash in the window. Every kilogram dedicated to slowing is a kilogram that could have protected systems, fed the crew, or increased payload. To reach another sun is only half the problem. To arrive safely is the other half. Interstellar travel forces us to admit a simple truth. Propulsion is not defined by engines, but by mass. The laws of momentum do not care why we fly, only what we carry. Every designer must choose between a ship that moves slowly but steadily, or one that burns brightly and pays heavily. Between them lies a frontier where physics does not negotiate. It only demands an answer to a single question: how much weight are we willing to lift across the night? Magnetic fields bend charged particles, guiding them away from hull and crew. Designing such a shield is like sculpting space itself, projecting a bubble that repels radiation and interstellar ions. Unlike thick armor, fields add no mass, but they demand power and stability. At high velocity, distortions ripple through the protective cocoon, testing the systems meant to preserve it. If humans cross to Proxima b, shielding will not be a luxury, it will be the boundary between vulnerability and survival. The principle is straightforward. Accelerate charged particles, and they curve according to the strength and direction of a magnetic field. Earth does this every second. Solar wind streams toward our planet, only to be deflected by the magnetosphere, a vast, invisible shell created by the motion of molten iron in the core. Without it, ultraviolet and cosmic radiation would scour the surface, stripping the atmosphere and sterilizing most life. Spacefarers must recreate this effect artificially, not for centuries of geological time, but in real time as they cross the void. A spacecraft's magnetic shield cannot be planetary in scale. It must be engineered with coils and superconducting loops anchored to the vessel's frame. When energized, these systems create toroidal fields that arc around living compartments. Charged particles entering the zone follow curved trajectories, spiraling harmlessly away from areas where humans and electronics reside. Instead of thick walls, the crew receives a shaped emptiness, a space carved by physics rather than metal. But magnetic shielding has limits. Neutral particles do not respond to the field. A dust grain, uncharged and microscopic, can slip through unbent, striking the hull at relativistic speeds. Plasma waves generated by the ship's propulsion may distort the field, punching holes in its symmetry. High-energy cosmic rays may ignore the field entirely. Designers cannot rely on magnetism alone. They must combine it with sacrificial armor, radar-like detection, and the constant monitoring of particle flux. The stability of the shield is a delicate negotiation. To bend energetic ions with meaningful strength, superconductors must run at high current while remaining near absolute zero. Cryogenic lines circulate coolant, feeding magnet coils like arteries. Any thermal spike increases electrical resistance, forcing the coils to quench, shutting down to prevent catastrophic failure. A shield that drops in the wrong moment leaves the ship naked to radiation, exposing crew and reactor alike. Thus, the protection must be continuous, redundant, and self-healing. Magnetic fields also shape the interior of a vessel. Crew habitats sit inside regions where flux density is weak, allowing human nervous systems to operate normally. Too strong a field can induce electrical currents, affecting muscle signals and instruments. Medical bays, storage tanks, and control modules require careful placement so that their contents do not interfere with the coils. The ship becomes a kind of magnetized cathedral, every hallway, compartment, and conduit arranged with respect to invisible geometry. Velocity complicates every assumption. At 10% the speed of light, incoming particles gain energy proportional to the square of velocity. The shield must respond not to the environment it is passing through, but to the energies it creates by moving through it. Effects accumulate. Plasma wakes from the reactor engine, ionization trails in front of the bow, and electric charge across the hull skin. Each of these interactions alters the shape of the magnetic bubble. The field must adapt moment by moment, folding and reshaping to meet threats that did not exist seconds earlier. Even the psychological consequences matter. Crew members will not see the field or hear its hum. They will trust an unseen barrier while living meters from vacuum and radiation. Their survival rests on algorithms, power relays, and cryogenic lines that must never rest. The technology will be designed to feel routine, but routine never dulls the stakes. If humanity travels to Proxima b, shielding will not be decoration. It will be the skin of the vessel, the invisible frontier that stands between a living community and a universe that was never required to keep that community alive. A generation ship must be more than transport. It must be a functioning town. Crops require soil, water, and gravity-like spin. Air must be purified and recycled endlessly. Children must learn not only mathematics and language, but the engineering that sustains the vessel. Culture bends around function. People celebrate holidays in curved chambers, work beside hydroponic towers, and watch stars that never change. They are settlers of a place with no land. The interior of such a vessel is not arranged like a space station. It is shaped by rhythms of life, not by the shortest path between modules. Walkways trace gentle arcs. Living quarters cling to the outer rim of centrifuges, where rotational motion simulates gravity. Gardens are placed where airflow is strongest, their broad leaves trembling under artificial breezes. Light cycles mimic dawn and dusk, signaling circadian patterns that keep the body anchored to time. Every surface is deliberate. Acoustic panels to soften the hum of pumps, radiant heating floors to prevent cold pockets, windows that display star fields not as entertainment, but as constant reminders of motion. Unlike temporary habitats, a generation ship must teach itself to survive. Systems are not static. They must evolve alongside the people who maintain them. Water passes through filters, absorbs carbon dioxide in algae tanks, and returns purified for drinking or irrigation. Waste becomes fertilizer. Organics are composted, not discarded. The ship treats decay as a resource loop, not an error. Nothing is simply thrown away. In a closed world, moving through starlight, garbage is a myth. Food becomes culture. Families tend plots, trade their herbs, and compare yields from nutrient mixtures. Wheat grown in curved rows tastes different from wheat grown in stacked trays. Children learn the subtle cues of hydroponics. How roots respond to lighting cycles. How humidity changes with population density. How pollination must be coaxed by hand when wind no longer exists. The process of feeding themselves gives meaning to the journey. They are not passengers waiting to arrive. They are caretakers keeping harvests alive through space and time. Social life forms around maintenance. Instead of sports stadiums, communal areas host demonstrations. A repaired heat exchanger, a new strain of lettuce that tolerates low light, an upgraded oxygen membrane. These achievements replace trophies. The vessel's shared pride is built from function. When a teenager learns to monitor reactor coolant or calibrate agricultural LEDs, they are praised not for ambition, but for safeguarding continuity. Education adapts to necessity. Children attend classrooms that overlook reactor shielding or greenhouse decks. Their textbooks describe stars and oceans, but their lived environment is valves, sensor readouts, and radial corridors. Elders teach them lessons grounded in responsibility. How to spot fatigue in a hull seam, how to handle vacuum suits, how to respond to pressure alarms. Their skills form a generational chain, each link transferring knowledge that will be vital long after its originator is gone. Psychology bends to scale. The stars outside barely shift over decades. Communities invent rituals to mark the passage of time. Orbit festivals that mimic seasons, anniversaries of the launch, rites marking transitions from student to caretaker. These practices are not nostalgia, they anchor identity. Without them, life drifts like the ship itself, directionless. Birth and death reshape the vessel. Each new child is a demand on resources, each passing elder a loss of experience. The ship must adapt its population carefully, expanding gardens or opening new living quarters. Leadership councils manage these decisions, not as abstract policy, but as daily logistics. Misjudgment is not political, it is existential. A generation ship is a paradox. It moves forward at immense speed, yet internally it feels unchanging, like a village preserved beneath glass. Its inhabitants are pioneers who may never see landfall, yet everything they do shapes the arrival of descendants they will never meet. Life inside such a world is not a waiting room, it is a civilization carried across the stars, committed to survival through discipline, memory, and purpose. In interstellar space, repair is not optional, it is routine. Bearings wear down, seals fracture, electronics degrade under radiation. Tools must carve replacement parts from raw stock or melt recycled metals into new forms. A damaged radiator is not a minor issue, it is a crisis that can cook the ship from within. Crews must practice a form of resilience that borders on craftsmanship, ensuring that every system outlives the people who maintain it. Even the most carefully engineered components fail. Polymers become brittle under cosmic rays. Insulation delaminates after thousands of thermal cycles. Microfractures creep through metal joints and expand with vibration. On Earth, these problems are solved by replacement and procurement. Spare parts arrive from factories, repairs occur in climate-controlled bays. A starship has no supply chain. The factory must travel with the crew, and its products must match the standards of the original builders. Workshops on an interstellar vessel are not symbolic. They are lifelines. Their machines run for decades. Cutters that etch new circuit boards, furnaces that melt scrap into fresh alloy, robotic arms that print structures layer by layer. The engineers are not mechanics who change parts. They are artisans who understand why parts fail and how to coax longevity from materials that originated under Earth's gravity but now endure the stresses of fractional sea flight. Material science becomes as important as navigation. A single weld made in haste can create a flaw that spreads silently over years. Every bolt is tightened with calibrated torque, every gasket chosen for its resistance to vacuum and radiation. Maintenance logs are encyclopedias, not checklists. They track cycles, stresses, temperatures, and tiny deviations. A red line in a logbook is not paperwork, it is the first whisper of disaster. The rhythm of repair shapes daily life. Crew members learn to diagnose by sound, the way a pump hums when its bearings wear thin, the pitch of cooling fans when filters clog. They notice changes in smell, ozone tripped by arcing wires, the metallic tang of overheated steel. Sensors warn of danger, but instincts prevent it. Just as farmers read soil, engineers read machinery. The act of listening becomes as vital as breathing. Radiation accelerates decay, semiconductor junctions drift, memory bits flip spontaneously, control boards fail without warning, shielding slows the damage but cannot stop it. Critical systems exist in nested redundancy. Triple flight computers, mirrored power rails, valves with manual overrides. The goal is not to make systems immortal, it is to prevent any single break from cascading through the ship. Redundancy is not inefficiency, it is survival protocol. Even successful repairs have consequences. A new pipe may disrupt airflow, altering moisture in hydroponic bays. A reprinted fan blade may vibrate at a frequency that intersects with living quarters. Machines become part of the ecosystem, and the ecosystem reacts. Engineering decisions ripple outward into agriculture, medicine, and psychology. On a world of steel, every action is communal. Eventually, ship and crew age apart. The original builders retire or pass away. Their apprentices inherit the tools and techniques. The vessel becomes a tapestry of generational choices. Original hull plates beside additive manufactured replacements. 60-year-old radiators patched by hands that never knew Earth. Continuity lives not in hardware but in memory, the shared discipline of tending machines that must never sleep. Failure at relativistic speeds is unforgiving. A coolant pump that falters for 10 minutes can overheat reactor shielding. A torn radiator wing can raise internal temperatures until power systems throttle. A stuck bearing can ruin a centrifuge, collapsing artificial gravity and disrupting food production. There is no safe harbor to drift toward, no workshop waiting in orbit. Repairs must begin where the problem occurs, with the tools available and the people present. To survive the crossing to Proxima b, a starship must be more than a marvel at launch. It must be maintainable for centuries, flexible enough to adapt, and humble enough to accept that entropy cannot be defeated, only managed. Machines will outlive their makers not because they are indestructible, but because each generation chooses to mend them, again and again, against the silence of the void. Passengers born en route to Proxima would inherit a mission they never chose. Their first steps would fall on curved decks, not soil. Their first view of the sky would be filtered through composite shielding. Their decisions would steer a world built by those long gone. How do generation ships govern themselves? Who grants permission for children to exist in a place they may never escape? These questions shape not only the future crew but the meaning of exploration itself. The architecture of a generation ship begins with steel and fusion chambers, but it continues with sociology. The first generation, those who volunteered, leave Earth with intention. They know the risk, the duration, the possibility. They will never see destination or return. Their lives unfold under centrifugal gravity, illuminated by artificial suns, surrounded by recycled water and air. To them, the vessel is not confinement. It is the entire horizon of existence. This perspective grants them ownership, yet it was not consented to. The ship becomes a philosophical paradox, a society created by choice that must be lived without it. No charter can anticipate every ethical dilemma. Birth rates must be regulated to maintain resources. Education must prepare children for roles they did not select. Autonomy must exist within boundaries determined by physics, not politics. A ship cannot double its population simply because hope rises or ideology shifts. Crops, oxygen yield, reactor output, these define the limits. The second and third generations inherit these parameters as unchangeable laws, even if they resent them. The mission is not oppressive by intent, only by constraint. Governance evolves in response. Councils may rotate leadership to prevent dynasties, or they may adopt merit-based systems that elevate engineers and biologists above charismatic voices. Some vessels might vote, others might follow a constitution laid down on Earth. Whatever form emerges, it will operate under continual pressure, steering a fragile environment where conflict is not symbolic but material. A dispute about power allocation or crop usage is not ideological debate, it is a question of survival. The ethics stretch further. Suppose a young adult refuses their assigned duty in reactor maintenance or hydroponics. They want to study art, or history, or simply live free of obligation. On Earth, such desires are accommodated by institutions or markets. On a generation ship, personal defiance may jeopardize the entire community. What is freedom when every hand is needed to keep atmosphere breathable? How does a society teach children that responsibility is not punishment, but the mechanism by which they remain alive? Then there is the question of destination. After centuries, a ship may arrive at Proxima only to find the planet inhospitable or already settled by autonomous probes launched centuries later from Earth. Do the descendants continue onward? Do they attempt to terraform? Do they abandon the mission and remain in orbit, circling a sun they never asked to reach? The crew must craft their own answers, not inherit those of ancestors long dead. Ethical considerations extend to memory. Some argue that each generation should know Earth intimately, its oceans, forests, and storms, so they understand what they are traveling for. Others suggest severing nostalgia early, replacing Earth's mythic pull with a culture built purely on board. Children raised without emotional anchors might accept their environment more readily, but they risk losing the empathy that connects them to the species that launched them. Even the act of departure holds ethical weight. A generation ship is not an expedition, it is a commitment that binds unborn people. Engineers can model engine efficiency and radiation shielding, but no calculation predicts the moral demands of a life carried across the void. The ethical foundation cannot rest on technology alone. It must rely on humility, transparency, and a recognition that exploration, when measured in centuries, becomes a question of stewardship, not conquest. In the end, the ethics of inherited voyages may define humanity's legacy more than the propulsion that moves us. Reaching Proxima b is an engineering challenge. Living justly while traveling there is a human one. A probe traveling at 20% of light speed would approach the Proxima system like a meteor. Slowing down would require as much energy as its entire acceleration phase. Most designs do not try. They perform a flyby, capturing images and readings as they streak past planets and debris belts. The encounter might last hours or minutes. Then the probe disappears into darkness. Visiting another star does not always mean arriving, it can mean witnessing. The idea is uncomfortable because exploration is usually imagined as arrival. We picture landings, footsteps, flags, orbiters establishing permanence. It treats the star not as a destination but as a moment. At relativistic speeds, engines cannot simply flip and fire in reverse. Momentum becomes a tyrant. The same acceleration that brought the probe across 4 light years now forces it onward like an arrow released from a bow. The spacecraft becomes a traveler that does not slow for scenery. To scientists, this is not failure, it is opportunity. A probe racing through the Proxima system gathers data with an urgency unknown in planetary missions. Telescopes and magnetic sensors capture snapshots of magnetosphere interactions. Spectrometers sample exoplanet atmospheres as fragments in reflected light. Cameras fire sequences in rapid bursts, milliseconds apart, hunting for storms, volcanic plumes, or rings of dust. The mission becomes a single long breath. Everything learned must be collected before the ship slips back into interstellar night. Designing instruments for this moment is as important as building the propulsion that delivers them. Sensors must react instantly and withstand harsh radiation and dust impacts. They cannot rely on real-time commands. Every action must be automated: point, measure, store, repeat. Imaging systems must compensate for relativity. Stars shift position as light bends around lenses at extreme velocities. Algorithms anticipate the distortion and correct for it. The results are imperfect, but they are more than Earth could see from afar. Deceleration, if attempted, becomes its own mission. To slow a probe moving at 0.2 c would require energy equivalent to the initial boost, plus reserves. Solar sails could be turned against the light of the destination star, but Proxima is a dim red dwarf. Magnetic braking could interact with stellar winds, but the drag is weak and unpredictable. A ship could deploy vast radiators to bleed kinetic energy as heat, but doing so risks catastrophic structural strain. Every option resembles surgery without anesthesia possible, but terrifyingly unforgiving. The trade-off forces clarity. A flyby mission narrows its objective. Acquire first-hand knowledge where telescopes cannot see. Confirm whether Proxima b has an atmosphere. Measure surface temperature. Detect water vapor, methane, or carbon dioxide. Observe the star's violent flares, which may scour the planet's surface or strip away protective layers. What would take Earth-based observatories decades of inference becomes minutes of direct observation. The encounter leaves the probe changed. Dust strikes have accumulated, sensors have degraded, power reserves thin. Its instruments may continue to broadcast, but every hour increases the chance of failure. Mission planners accept this. The craft's life was never measured in years, it was measured in moments of contact. After the pass, telemetry becomes its legacy. Humanity may receive these transmissions long after the probe has vanished beyond tracking range. The data will arrive pixel by pixel, signal by signal, slowed by light time. Researchers will analyze spectra, compare measurements, argue over temperature gradients and atmospheric signatures. The probe itself will be silent, continuing its endless drift into a region of space no one will follow. A flyby mission does not fulfill our romantic vision of exploration, but it honors physics. The universe does not bend to our expectations. We must adapt to its consequences. At relativistic speeds, visiting Proxima is not a landing, it is a glance. And for a civilization that has never seen another sun up close, a single glance may be enough to change everything. Orbital capture is expensive. To break into a stable orbit around Proxima b, a spacecraft must shed most of its speed. Braking sails, reaction mass, or gravitational assists become tools of necessity. Every kilogram dedicated to deceleration replaces payload, shielding, or life support. Designing a mission around arrival forces a harsh trade. Less science, more fuel. Fewer instruments, more propellant. Exploration becomes an equation written in mass and patience. Arrival is not a symbolic milestone, it is a change of energy. A ship traveling 0.1 or 0.2 times the speed of light carries kinetic energy so vast that it dwarfs every onboard system. The velocity that makes the journey possible becomes the barrier that prevents orbit. In interstellar terms, slowing down is not like pressing a brake pedal. It is more like trying to extinguish a star. All of the momentum must be dissipated either as heat, radiation, or exhaust. Physics does not care that the destination is finally in view. One proposed method mirrors the launch approach of laser sails. Turn the sail around and let starlight push back. Its photons trickle outward, they do not shove. A braking sail would need to be immense, fragile, and perfectly aligned for years. Any tear, wrinkle, or twist could send the craft tumbling. The ship must endure constant micrometeoroid strikes while presenting the largest target area possible, a paradox of fragility and exposure. Reaction mass offers more certainty. Fire an engine in reverse, ejecting propellant to slow the vessel. But the rocket equation is merciless. Every kilogram used to decelerate must be accelerated in the first place. Carried fuel becomes dead weight during the outbound journey, and twice as expensive energetically. A mission built for arrival often resembles a snake swallowing a city tank after tank of inert propellant waiting to be burned in the final act. What survives at the destination may be far smaller than the ship that left Earth. Gravitational assists, which serve spacecraft so well inside the solar system, lose their power when only one star lies ahead. No Jupiter or Saturn waits to lend a slingshot boost or steal momentum. There is only Proxima b, with its narrow sphere of influence, and Proxima Centauri itself, a modest well of gravity compared with the Sun. A ship traveling at relativistic speeds sweeps through those wells too quickly to make meaningful use of them. Gravity becomes scenery, not a tool. Some designs imagine braking against the thin medium of interstellar space. Magnetic sails unfold behind the ship, interacting with charged particles in the void. The vessel drags against the gas, bleeding speed into the environment. Theoretically, this could work over decades. Practically, the pressure is so faint that the sail must span kilometers and still might take years to shed a few percent of velocity. Any misalignment risks structural collapse. The interstellar medium becomes both brake pad and grinding stone. Arrival, therefore, becomes a question asked at launch. Do we intend to stop? If not, the mission can remain lean. Sensors dominate mass. Engines vanish. But once arrival matters, once boots or delicate robotic landers are part of the plan, everything changes. Payload shrinks to make room for propellant. Shielding thins to reduce weight. Scientific instruments are stripped down to what is strictly necessary. Travel becomes a sacrifice made long before departure. The cruelest irony is that most of the work is done when the destination is already visible. After 40 light years, 40 years of flight, or 40 decades aboard a generation ship, the final kilometers are the most expensive. Failure to slow means missing the target forever. There is no second loop, no safe return. The ship will rush past the red glow of Proxima b and fade into darkness. Arrival is the moment exploration ceases to be a dream and becomes a negotiation with reality. It demands energy equal to ambition. And in interstellar space, ambition is measured not in courage or curiosity, but in mass, the one resource the universe never lets us ignore. At high velocity, clocks aboard the ship fall out of sync with clocks on Earth. A crew traveling near light speed might experience only a few years while decades pass outside. Time dilation is not science fiction, it is a measurable consequence of relativity. Journeys to Proxima b may one day distort human timelines, separating travelers from the societies they left. They would return to a future that remembers their departure as history. Time dilation is not a metaphor. It is a physical law rooted in motion and energy. As speed increases, kinetic energy reshapes how events unfold inside a moving frame of reference. To the crew, days feel normal. Heartbeats tick in rhythm, meals arrive on schedule, crops grow in greenhouse rows, but onboard time no longer matches the time of Earth. The faster the ship travels, the more the difference widens. What appears as a year under relativistic acceleration may become 3, 5, or 10 years for those who stayed behind. The effect is subtle at low speeds. A Mars mission or a journey to the outer planets barely changes the clocks. But as velocities approach a significant fraction of the speed of light, 0.3 c, 0.5 c, 0.9 c, the separation becomes profound. A crew traveling at 90% of light speed could reach Proxima b in less than 5 years of Earth time, but they themselves might age scarcely 2. Their spacecraft becomes a bubble of compressed chronology, drifting through the long stream of history. Relativity gives no warnings. There is no sensation that time is bending. The ship's chronometers tick evenly, conversations unfold without distortion. Only when signals arrive from Earth do travelers notice the gap. A recorded message from family stored in the ship's archives, sent 1 year after departure, might reach the crew 3 or 4 years later after they themselves have experienced half that time. The exchange becomes asymmetric, a dialogue in which the participants live at different speeds. For those left behind, the effects are emotional. A parent watches a child step onto a launch platform, then sees their face again only after decades, unchanged by age. The traveler returns as the same person who left while everyone they once knew has lived through a lifetime. Generations can pass while the crew remains physically young. Relativity turns journey into exile, not because distance separates the explorers, but because time does. The consequences extend beyond families. Political systems evolve. Nations shift. Scientific understanding leaps forward. A crew trained on the technologies of 1 century may return to a world that has rewritten its assumptions. They could be greeted not as heroes, but as relics representatives of an earlier era whose views and knowledge no longer align with the culture they return to. The timeline of the ship is small and personal. The timeline of Earth is broad and unbounded. Communication strategies must adapt to this divergence. Messages sent from the ship arrive on Earth after delays measured in years. Earth's responses, shaped by societies that have changed during that time, arrive with new expectations and priorities. Mission control becomes a historical archive. Records past explorers consult as guidance rather than a living authority. Autonomy is not only practical, it is required by chronology. This disparity also reshapes ethics. A ship's crew may be viewed as living ambassadors to the far future, even if they never intended to be. Their children might inherit values preserved in isolation, untouched by social shifts back home. Travelers in high-speed vessels become custodians of an older worldview not because they resist change, but because they outran it. They are explorers who carry one timeline through another. The physics does not punish them. It simply applies the rules of motion. Space does not care how humans measure months or generations. It enforces a truth, that time is not universal, and speed bends it like gravity bends light. When a crew approaches Proxima b, their arrival marks more than a geographic crossing. It marks a fracture in history, one human timeline splitting into two, never perfectly reunited. When matter meets antimatter, both vanish, releasing pure energy. No chemical reaction comes close, and even fusion pales beside it. A gram of antimatter carries the destructive power of tons of TNT. Harnessed, it could push a ship to half the speed of light. But storing antimatter is like holding lightning in glass. Stray particles annihilate walls and machinery, demanding containment that has not yet been engineered. Potential and peril coexist in every microgram. Antimatter is not fantasy. Laboratories on Earth produce antiprotons and positrons routinely, though only in microscopic quantities. They appear briefly, caged in electromagnetic bottles, then collide with ordinary matter and vanish in bursts of radiation. Scientists detect the consequences: gamma rays, decay trails, and plot them like fingerprints. These experiments prove the principle. Annihilation is real, measurable, and terrifyingly energetic. The challenge lies not in generating it, but in storing it long enough to matter. A spacecraft built around antimatter propulsion would resemble a vault before it resembles a rocket. Containment cages would float particles inside magnetic fields, ensuring no atom touches the walls. The fields must be stable for years at a time, unaffected by vibration, radiation, micrometeoroid strikes, or temperature swings. If a coil fails, the antimatter drifts millimeters and strikes ordinary matter. The resulting blast is not a malfunction, it is a detonation. A milligram could shred the ship, and yet the rewards tempt engineers. Fusion engines consume grams of fuel per pulse to accelerate to 0.1 C. The ship shrinks from a colossal factory to something elegant. Tanks of hydrogen for reaction mass, small stores of antimatter to energize it, and magnetic nozzles to direct plasma exhaust. The dream is simple: maximum energy, minimum mass, the purest efficiency ever conceived for motion. But the physics of annihilation is indifferent to dreams. The gamma rays produced in the reaction bombard the engine and everything behind it. They travel through materials with ease, damaging electronics and irradiating crew. Thick shielding can deflect them, but shielding adds mass. The more mass in armor, the slower the ship accelerates. Thus, the engine becomes a balance between protection and performance. Too little shielding, and the crew is cooked. Too much, and the vessel crawls. Heat adds another complication. Antimatter reactions produce not only light but charged particles that must be funneled through nozzles. If they escape confinement, they embed themselves in hull structures, releasing energy in unpredictable patterns. Every pulse becomes a test of precision magnetic geometry. Even slight misalignments accumulate stress over years of operation. A generation ship can afford inefficiency, an antimatter craft cannot. There are proposals to neutralize the risk. Some designs suggest creating antimatter only as needed, synthesizing it from reactor output and annihilating it immediately. Others propose storing antimatter in chemical bonds, antimatter molecules paired with matter in exotic cages. But these ideas remain theoretical, dependent on materials that exist only in equations. The engineering horizon has not caught up to the physics. Beyond hardware lie questions of responsibility. Who decides to carry a cargo that can obliterate a vessel with a single leak? Who trains crews to maintain chambers that must never see dust, never suffer corrosion, never experience an electrical surge? A miscalculation becomes more than a failure. It becomes a tragedy multiplied by its speed. The crew of an antimatter ship lives beside power equal to their survival and their destruction. Still, the promise endures. Nothing known to humanity offers such energy density. Nothing shortens interstellar travel so dramatically. If one day travelers reach Proxima b in single-digit years, their engines may be fueled by the annihilation of matter itself, small seeds of stored starfire harnessed with absolute discipline. Antimatter propulsion is not hope or hazard alone. It is a union of both, waiting for a civilization willing to balance them. Humans are social animals. We anchor our lives to seasons, sunlight, and shared rhythms. In interstellar transit, these anchors vanish. The stars outside do not move. The hum of life support becomes the clock. Isolation carves new psychological landscapes. Communities must invent rituals, celebrations, learning cycles, shared projects to maintain identity. Space travel is not simply endurance of distance. It is endurance of meaning. Inside a starship, time does not pass the way it does on Earth. There are no storms or sunsets, no wind through trees or shifting tides. The environment is constant, engineered to be reliable because failure has consequences. The result is a world that feels static. Days stretch into indistinguishable sequences of maintenance checks, agricultural shifts, and sleep schedules. Without intentional structure, monotony erodes motivation. The crew must manufacture variety moments of celebration to balance the quiet, spaces for reflection to balance the grind. Artificial day-night cycles help. Lights warm and brighten in the morning, dim and cool in the evening, echoing the rhythms of their distant homeland. Alarms mark the passing of hours, not because darkness falls, but because the mind needs punctuation marks to understand its own continuity. A vessel crossing the void cannot rely on nature to set tempo. It must create its own metronome. Culture becomes infrastructure. Holidays celebrate system upgrades or anniversaries of departure. Birthdays become communal events. Adults teach children about earth oceans that crash against beaches, skies that fade from blue to red at dusk, not because children must long for them, but because memories protect mental elasticity. Even if the youth never step on soil, knowing that soil exists gives their world context. Work, in such an environment, is not merely employment, it is identity. Farmers become guardians of oxygen. Technicians become custodians of gravity. The smallest duty, tending algae mats, filtering grey water, monitoring radiation levels, becomes a contribution to survival. People do not labour for a wage, they labour for continuity. The psychological anchor is not salary, but purpose. The absence of that purpose becomes dangerous. Conflict, when it emerges, cannot be ignored. Personal grudges slip into maintenance lapses or sabotage. Interpersonal tension becomes environmental tension. Leadership must intervene early. With fairness and transparency, dispute resolution becomes as critical as reactor operation. The health of minds is the health of machinery. Isolation magnifies loss. A death is not a number on a registry, it is a friend gone from the dining table, a mentor absent from the greenhouse, a voice no longer heard in morning shifts. There is no cemetery outside, only memorials carved into bulkheads or digital archives of voices preserved for future generations. Grieving aboard a starship becomes communal, silence is shared, and so is recovery. Children born in transit inherit a psychological horizon defined by metal and stars. Their play occurs in centrifuge parks. Their drawings depict ring corridors rather than forests. For them, The void outside is not frightening. It is home. Adults might mourn the Earth they left. Children do not. They map their dreams onto corridors, hydroponic gardens, and lecture rooms. Spaceflight becomes normal because they have never known anything else. Mental resilience requires more than routines. It requires meaning that persists across generations. Young adults must believe their work matters to people they will never meet. Elders must trust those who replace them. Teachers must cultivate imagination without breeding despair. The ship must be a vessel for purpose as much as it is a vessel for propulsion. In interstellar flight, the body adapts to artificial gravity. Machines adapt to long wear. But minds must adapt to a life lived inside an engineered horizon. The deep is not dangerous because it is dark, it is dangerous because it is silent. Civilization must fill that silence with connection. Only then can human beings remain themselves across the empty years between stars. The Milky Way is not still. Stars orbit its core at different speeds, drifting like continents on a molten mantle. A spacecraft must chart not just where Proxima b is, but where it will be decades or centuries from now. Sensors and models must adapt to stellar motion, interstellar gas flows, and the subtle gravity of passing stars. Navigation becomes a discipline of predictive thinking, seeing not the present, but the future path of a destination. In deep space, a target star is not a fixed beacon, but a moving object with its own orbit and velocity. Proxima Centauri drifts around the galactic center, pulled by a mixture of visible matter and the unseen mass of dark matter. A ship launched today cannot simply point toward its coordinates. It must aim toward a future position, correcting for how Proxima will move as Earth circles the Sun and the entire solar system sweeps around the galaxy. A journey of decades or centuries forces navigation to behave like astronomy in reverse. Instead of tracking stars, we must anticipate them. This is more than charting coordinates. The vessel travels through a medium filled with gradients of gravity, each one exerting a small tug. Passing stars exert faint forces, barely noticeable in a human lifetime, but meaningful over light years. Interstellar clouds, thin wisps of hydrogen and dust also influence trajectory. Their mass is subtle yet persistent. A course left uncorrected may drift by millions of kilometers, enough to turn a planned arrival into a miss measured in astronomical units. Navigation systems must therefore operate continuously, comparing expected positions to observed ones. Sensors read Doppler shifts in starlight, measuring how the frequency of light changes as the ship moves. Atomic clocks internal to the vessel calculate time more precisely than any human eye could. Even slight shifts in spectral lines help determine whether the ship is accelerating or drifting. Navigation becomes a conversation with photons. The universe speaks through starlight, and the vessel answers by altering its course. On Earth, maps are anchored. Mountains do not migrate, oceans do not change their orbits. But in space, motion is the baseline. Every star is a traveler, every dust cloud a tide. To guide a ship across this terrain, models must behave like weather forecasts. They incorporate not only known data, stellar locations, velocities, distances, but the uncertainties around them. No simulation remains perfect for half a century. Updating models becomes as crucial as maintaining engines. Even communication affects navigation. Signals returning from Earth arrive after years. They describe what Earth thought the ship should do, not what the ship encounters in the moment. Relativistic effects distort star positions further, shifting light as velocity increases. Instruments must account for this bending of perception, correcting for a universe that looks different at 1/10 light speed than it does at rest. Pilots, whether human or artificial, navigate not through what the eye sees, but through what the equations reveal. Redundancy becomes non-negotiable. Multiple star trackers cross-check each other. Gyroscopes stabilize attitude. Long baseline interferometers compare distant sources, using their relative angles like triangulation points. If one system falters, another takes the load. Navigation is not a singular calculation, it is an ecosystem of sensors working in harmony. The final challenge is time. A ship reaching Proxima b at 0.1 c may see its target's orbital path shift significantly. A massive flare could expand the atmosphere of Proxima b or distort its magnetosphere. A planet thought to exist might vanish behind new data. Navigation does not end when the ship approaches the star, it intensifies. Course corrections become sharper, more frequent, because every kilometer matters. Guiding a ship to another sun is not simply plotting a route. It is learning to think in epochs, predicting the future geography of a galaxy that never stops moving, and steering through it with humility, precision, and patience. Beyond certain speeds, physics becomes the adversary. At half the speed of light, the kinetic energy of a ship rivals nuclear detonations. Dust behaves like weaponry. Heat accumulates faster than radiators can shed it. Life support strains. Payload shrinks. Concepts that promise high velocity reveal their costs in shielding mass, radiator surface, and catastrophic risk. Ambition collides with material limits, forcing compromises. As velocity increases, the spacecraft's surroundings change in ways no pilot has ever experienced. The stars do not move, but their light bends, compressed into a blue-white glare ahead and stretched to red behind. The cosmic microwave background, once a faint whisper of radiation, becomes a wind of energetic photons. Interstellar hydrogen, so diffused that a cubic meter in space may contain only a few atoms, becomes dense enough at relativistic speeds to strike with the force of a storm. A ship traveling near light speed is not merely fast, it is in a fundamentally different environment. Shielding becomes the first line of defense, and its demands grow exponentially. The hull must endure not occasional impacts, but millions of micro-collisions per minute. Designers imagine layered armor that vaporizes incoming grains, turning them into harmless plasma clouds. But every additional plating increases mass. Increasing mass reduces acceleration. Reduced acceleration extends mission time. The push for speed always drags a penalty behind it. Heat follows close behind. At 0.5 C, the ship plows through particles fast enough to generate immense thermal loads. Even if collisions never breach the hull, they add energy that must be expelled. Radiators, already expansive at modest speeds, must grow into wings and lattices stretching across the vessel. They glow continuously, bleeding infrared into the void. But radiators cannot be too exposed, or they become targets for dust strikes. They cannot be too small, or the ship suffocates in its own waste heat. Every design is a negotiation between surface area and vulnerability. Radiation protection intensifies these conflicts. Cosmic rays, normally scattered by Earth's magnetosphere, slam directly into the ship at energies humans rarely encounter. They slice molecules, ionize electronics, and decay structural materials. Water tanks or hydrogen-rich polymers can protect living quarters, but they add weight. Magnetic shielding can bend charged particles, but fields require power, superconductors, and cryogenic systems. The faster the ship moves, the more elaborate and fragile its defenses must become. Propulsion itself becomes burdened by relativistic energy. At a tenth of light speed, momentum is formidable. At half, it becomes dangerous. The amount of energy required to accelerate further increases not linearly, but sharply. Engines that once seemed powerful now strain. Even fusion begins to look insufficient. The vessel becomes a paradox, a machine built to move quickly, yet slowed by the protections needed to survive its own velocity. Life support faces quieter challenges. High-speed travel amplifies every failure. A clogged filter or a cracked pipe is not a repair to schedule, it is an existential threat. Plant bioreactors rely on delicate environmental conditions, which vibration and thermal variance disrupt. Crew habitats must remain stable, despite constant bombardment of micro-impacts and electromagnetic interference. Without perfect equilibrium, food production falters and oxygen yields decline. A crude relativistic vessel is not only a ship, it is an ecosystem under siege. Then there is the question of safety margins. Interstellar travel at extreme speed leaves little room for error. A misaligned sensor, a failing magnetic coil, an unexpected region of dense dust, any deviation magnifies into catastrophic consequences. Unlike slow vessels, relativistic ships cannot coast to a halt. They are bound to their trajectory. The momentum they have gained cannot be casually discarded. For engineers and astronauts, these realities form a boundary, not a wall, but a horizon of practicality. Physics does not forbid high velocity, it taxes it. Ambition pushes towards speeds approaching light, but the universe replies with cost, kinetic energy, radiation, heat, risk. At some point, the dream of outrunning time becomes indistinguishable from attempting to outwit the laws that shape existence. The edge of relativistic ambition is not where speed becomes impossible. It is where speed stops being survivable. Warp metrics propose another path. Manipulate space-time itself. A bubble forms around the craft, compressing distance ahead while expanding space behind. Inside, the ship moves gently. Outside, the bubble translates faster than light. The physics exists on paper, but the requirements remain extraordinary. Exotic energy densities, negative pressure states, materials never observed in nature. Warp flight is a frontier of equations, not engineering, a reminder that mathematics can outrun our tools. Einstein's relativity does not forbid faster than light travel. It forbids motion through space-time faster than light. Warp metrics exploit a loophole. Change the shape of space-time itself. Like placing a rug under a glass and pulling it from one side, the craft never breaks the speed limit, it simply rides geometry. In models such as the Alcubierre drive, the ship sits motionless inside a protected region, a pocket where time flows normally. Space expands behind the vessel, contracting in front, pulling the bubble forward. Nothing inside the bubble experiences acceleration, g-forces, or relativistic distortion. The crew could sip tea while crossing light years. But every equation contains an assumption, and here the assumptions are brutal. To compress space-time, the bubble walls must contain negative energy density, something no laboratory has produced at macroscopic scale. Quantum fields can briefly display negative values in vacuum fluctuations, but those phenomena exist as tiny whispers, not sustained reservoirs. Warp calculations require energy densities rivaling the mass of planets. If they could be gathered, they would need to be controlled like a sculptor shapes clay, forming a stable torus around the vessel while preventing space-time from tearing. Even imagining containment raises new questions. How does a ship enter or exit its bubble? How does it steer? If a bubble forms without careful shaping, it might collapse or expand uncontrollably. Once formed, it may be blind to its surroundings. Everything outside the shell is causally disconnected from the interior. A ship traveling faster than light cannot see what lies ahead. Asteroids, dust clouds, even entire worlds might exist in the path, yet no warning reaches inside until the bubble collapses too late to avoid disaster. Energy extraction compounds the difficulty. A spacecraft must manipulate curvature without destroying itself. Power systems capable of generating the required stress-energy tensor would dwarf any known reactor. Antimatter engines, even if perfected, are insufficient. The bubble would demand negative energy on scales far beyond conventional mass energy conversion. Dark energy, the force accelerating the universe's expansion, hints at the type of physics required, but no one knows how to harvest or shape it. It is a cosmic phenomenon, not an engineering material. And yet progress occurs in the margins. Theoretical physicists search for warp geometries with reduced energy demands. Some propose changing bubble shapes to lower the cost. Others suggest using metamaterials or quantum vacuum manipulation. A few designs redistribute strain to the edge of the bubble, shrinking the impossible into the merely implausible. Each paper inches closer to feasibility, but only on chalkboards and simulation grids, nowhere near a construction bay. Even if the energy problem were solved, society would face consequences as profound as the engineering. A civilization capable of bending space-time could cross interstellar distances in days rather than lifetimes. Borders would lose meaning. recording history would require new calendars. Trade, migration, diplomacy, all would stretch beyond planets and stars. Human identity itself would bend, as families live across stellar systems like modern cities separated by oceans. Warp travel is an expression of audacity. It asks not how fast a ship can push against space, but whether space can be taught to move around the ship. For now, the answers exist only as symbols in notebooks, as metrics in physics journals, as thought experiments passed between theorists. The mathematics may be sound, but engineering lags centuries behind. And so warp remains a horizon of possibility, a reminder that sometimes the most ambitious paths are the ones we cannot yet walk. If a warp vessel maintained an effective speed of 100 times light, the journey to Proxima b would collapse from centuries to days. The interstellar gulf would behave like a tunnel entered, traversed, and left with barely time to measure. Such concepts invite awe, but they must be protected from fantasy. Until the mechanism exists, they remain thought experiments, windows into futures that may or may not arrive. The scale of the transformation is difficult to grasp. Every previous method, fusion drives, laser sails, antimatter engines, must bargain with momentum and mass. Warp travel abandons that negotiation. It does not accelerate the ship, it reshapes the route. A vessel in such a bubble might experience quiet motion, no radiation storms, no months of acceleration burns, no dust impacts at relativistic speeds. The stars would not streak past. Instead, the universe itself would rearrange its geometry, compressing the gap between origin and destination. The passengers would not feel heroic, they would feel like travelers on a calm subway line. But a tunnel through space-time is not a neutral corridor. Space around the bubble would distort. Energy would gather in front and spill behind, like waves curling around the prow of a ship. The front edge could compress radiation into lethal frequencies. The rear might unleash bursts of energy as the bubble collapses, potentially sterilizing everything in its wake. Even in the best theoretical models, arrival must be choreographed with care. Warp travel risks not merely safety, but the environments of the worlds it visits. Navigation becomes a philosophical challenge as much as a technical one. When a craft moves through bent space-time, the universe outside the bubble is causally disconnected. The ship cannot see ahead. There is no ability to dodge. The vessel trusts the geometry it generated at departure. A warp jump is a decision made once, then carried to its conclusion. Mid-course corrections are not turns of a wheel, they are changes to the structure of space-time itself. Even a minor adjustment demands energy beyond the reach of current physics. And then there is the question of who travels. Humans are fragile organisms built for slow timelines. They age, they worry, they bond. A 2-week journey to another sun would feel almost absurdly mundane. The psychological weight of distance would vanish. What once required generations could be undertaken in vacation time. Science historians might debate whether such ease cheapens exploration or dignifies it. Colonization might become migration. Families could split between stars like modern families split between countries. The cosmos would gain neighborhoods. But ease hides its own dangers. If warp travel were possible, its power could bypass ethical guardrails. A civilization capable of reaching another star in days could also bring weapons, pathogens, or unregulated technologies across light years. Treaties would struggle to keep pace with capability. Contact between species, if any existed, could occur faster than governments or cultures could respond. Interstellar travel would shift from endurance to geopolitics, from engineering to diplomacy. Even without speculation, the practical questions remain enormous. Where does the energy come from? How is negative mass stabilized? What keeps the bubble intact as it passes through gravitational fields and magnetic sheaths? Every partial answer leads to another unknown. Warp concepts today are like gliders designed before metallurgy, beautiful ideas, insufficient materials. Still, they matter. Not because they are imminent, but because they extend our imagination honestly. They remind us that barriers are not always walls. Sometimes they are mirrors reflecting the limits of our tools. Warp is not a promise that humans will reach Proxima in 14 days. It is a challenge to consider what kind of civilization we would become if we could. It is an invitation to imagine a future where the distance between suns is not measured in lifetimes, but in journeys we might choose to take. Traveling 400 years or 15 days is not only a question of speed, it is a question of how we choose to meet the universe. Every propulsion method reveals a different aspect of ourselves: patience, engineering, risk, imagination. Proxima b is not merely a planet, it is a mirror. It shows the scale of our ambition and the limits of our understanding. Whether we drift slowly or leap in days, the journey asks the same thing. How far will humans go to learn what lies beyond familiar light? Each approach to Proxima carries its own philosophy. A generation ship embodies endurance. It asks hundreds of people to build a society on metal decks, tending gardens beneath artificial skylines, planting trees they will never sit beneath. Their success rests not on speed, but on continuity. They measure time in births, harvests, and repairs. The destination is not a finish line, it is a legacy handed to descendants they may never meet. In that model, the journey is the civilization. Fusion engines describe a different identity. They are tools of deliberate ambition. They postulate decades instead of centuries, powered by systems that mimic stellar hearts. Their crews accept hardship, radiation, and maintenance because progress is tangible. A star approach not in myth, but in lifespan. The fusion ship is humanity saying, "We will not wait for miracles. We will build them." It is engineering sharpened into purpose. Light sails, laser-driven, and gram-thin, show restraint. They prove that exploration does not require colonists or cathedrals of alloy. A sail moves knowledge instead of bodies. It accepts that a camera and a computer can gather truth as well as a human eye. The mission becomes modest and surgical: one craft, one glimpse, one return packet of data. It speaks like a whisper rather than a shout, yet it still crosses the gulf. Antimatter vessels demonstrate willingness to wield danger. They condense annihilation into fuel, converting grams into megatons. If such craft ever fly, they will be monuments to discipline. Precision fields balanced against obliteration. Devices that contain catastrophe in the name of speed. They reflect a civilization that trusts its calculations more than its fear. Warp concepts reflect something more abstract. They acknowledge that the galaxy is not merely a distance to be crossed, but a structure that might be folded. Warp vessels are not built on engines alone. They are built on mathematics that treat space-time as fabric rather than horizon. They ask whether the laws of nature can be collaborated with, instead of confronted. They are visions not of escalation, but of synthesis. In each case, Proxima b is the same, a dim sun with a rocky world orbiting it. The differences arise from us. Do we approach slowly, accepting that patience is the price of discovery? Do we accelerate ruthlessly, trading safety for decades? Do we send only machines, acknowledging that data is enough? Or do we attempt to bend space-time, asserting that distance is a boundary meant to be rewritten? The gulf between stars is not empty, it is instructional. It forces us to confront scale that dwarfs generations, materials that wear down, biology that falters, psychology that demands meaning. It shows why exploration is never just propulsion, it is governance, culture, ethics, and resilience. To cross it is to admit our limitations and attempt to transcend them anyway. When future historians describe humanity's expansion beyond the solar system, they may not focus on the destination. They will speak of the vessels, the crews, the engineers, and the societies that undertook the first great crossings. They will note the worldviews embedded in the drives and the decisions. The patience of multi-century voyages, the daring of relativistic craft, the precision of light sails, the audacity of warp. Proxima b is not valuable because it is habitable or close. It is valuable because it tests us. It asks whether curiosity is strong enough to compress lifetimes into missions, whether cooperation can sustain generations in motion, and whether imagination can become technology. The gulf is wide. The void is indifferent. But neither is reason to turn away. Crossing the distance is how humanity learns who it is, whether we are caretakers of fragile ships, builders of stellar engines, or dreamers who bend space itself. The route we choose will define us long before we ever see Proxima's red dawn. Between stars, there is distance, but not silence. Hydrogen drifts in long currents, cosmic rays thread through darkness, and gravity shapes the pathways of suns. We exist inside this structure, not apart from it. Our solar system is one eddy in a wider tide, circling the center of the Milky Way along with hundreds of billions of others. Proxima b is a nearby world by cosmic standards, but reaching it reminds us how vast nearby truly is. Across our journey tonight, we traced many paths. Some engines exist now: nuclear electric drives, fission thrusters, and ion propulsion. They are reliable, disciplined tools that teach patience. Others take us further: fusion probes, laser sails, antimatter drives, ideas that stand on the edge of engineering, demanding precision and resolve. And some remain wholly theoretical, warp metrics that bend space, bubbles of geometry instead of thrust. They belong to mathematics more than metal. We understand the physics that governs motion. We know how mass resists acceleration, how radiation erodes machines and flesh, how time itself stretches as velocity approaches light. But what we do not know is just as important. We do not yet know how societies endure centuries in motion, how minds evolve when entire generations live between stars, or how our view of humanity changes once another sun fills our windows. Exploration is not a single goal. It is a process of learning, testing, and refining. The first ships that cross the Gulf may be small, fragile, and focused on observation. Others may follow with families, greenhouses, and schools. Each will tell us something different about who we are and who we might become. Space does not promise answers. It offers opportunities to ask better questions. Thank you for exploring with me. Sleep well. Good night.